Okay, we will start now from 74th problem. So look at the problem. 74 is a problem from capacitors. See, the problem says you have here a capacitor of 4 microfarad, a capacitor out here of 3 microfarad, right? And then you have a capacitor here of 9 microfarad, and then you have one more capacitor out here. That value was given to you as 2 microfarad, and then you have here a battery that is giving you 8 volt of supply. And what is the question trying to tell you? It is telling you that if the whole charge that is on 4 microfarad and 9 microfarad capacitor is assumed to be a point charge located 30 meters from there, what will be the field? So what we need to do is we need to find the charge on this 4 microfarad capacitor and 9 microfarad capacitor, and we have to add it up. And then it is a simple problem of finding the field as kq by r squared. So now this is quite available. Now 9 and 4, these things are in question. First, they appear to be in parallel, so I can straight away write this combination can be reduced to 12 microfarad. Now this is 4 and this is 12, so 4 into 12 divided by 4 plus 12, that is 16. 4 and 16 gone, this becomes 4, so this is 3. So this whole combo here to this battery will look like a 3 microfarad capacitor. So the charge that will flow through this will of course be Q is equal to CV, so 3 multiplied by 8 will be 25 microcoulomb. So 24 microcoulomb is what is flowing through this. Now the potential across this and this will be equal. Okay, so what we do generally, we know Q equal to CV, and in this combination of the voltage is same on this and this, then Q should be in proportion to C. And what is the ratio of C? This is 3 and this is 9, so 1 is to 3. So the charge also will get divided in the ratio of 1 is to 3. So 24 if you have to divide into 1 is to 3 ratio, so what you do is you make 4 parts of it, so it becomes 6, 24 by 4, 6, give 3 parts to this and give 1 part to this, okay? So 24, 6 microcoulomb will be here and remaining 18 microcoulomb will be at this point. So 24 and 18, if you add it up, you get 42 microcoulomb. This will be the charge that this plus this will have. And what is the question telling you? The question is telling you that take this to be a point charge and find the field at a distance. How much? 30, right? And you know, if this is a point charge, the field will be 9 into 10 to the power 9 into Q. Q is 42 into 10 to the power minus 6. 30 meters square will be 9 into 10 to the power of 30, so 10 to the power 2, right? 30, okay, right. So now this 10 to the power 2, this term and this term will lead to 10, 3 and 2 gone, 6, okay, and 9 and 9 you can straight away lose. So you get 420. 420 is the value that you are getting for electric field. So the electric field at a distance of 30 meter will be equal to what? It will be equal to 420 Newton per coulomb, right? That will be the field you get, or volt per meter, whatever you want to give the unit. So the correct answer for this, if you see, the correct answer should be 420, that is 2. So the correct answer here will be 2. This is your problem number 74, as I said. Not so difficult, only you have to be a little careful while doing it. Now 75th question is a factual question. You don't have to worry about it. Simple Maxwell's rainbows question, that is your electromagnetic spectrum. You know what comes at the lowest end, radio waves, and what comes at the highest end, X-ray. And the frequency and the wavelength, if you look at the wavelength of blue light is smaller than the wavelength of yellow light. So the largest wavelength being that of the red. So the energy, if you look at it, the correct option straight away leads to 4, because radio waves will have smallest energy. E is equal to h nu, where nu is the frequency. Frequency of X-rays will be largest, right? Frequencies of X-rays will be largest. And then smallest, you have to arrange it in the order of increasing energy. The smallest increasing energy will be associated with radio waves, and the largest energy will be associated with X-rays. So D should be the first one, C should be the last one, but then there is only one option that satisfies that. So you don't have to look at others even. The fourth option will be a correct option. Okay, take two extremes. Radio waves will be smallest, and then comes the light. Light will be in between, and X-rays will have largest energy. Simple factual question. 76th question again is a factual question. You don't need to do any calculation in this. This is straight away. You are taught many times now that hysteresis curve, if you do it for, we did it in the class with steel and the soft iron. So what kind of curves you get? You get, this is the first time it happens like this, goes like this. Okay, this is your steel, and you are given two, but I am just recalling what we studied. Like soft iron comes out to be like this. And if you recall, retentivity of this is smaller, coercivity of this is more. You see, criteria is what? When you are using when you want to make permanent magnets, you use steel because you are looking for highest retentivity and highest coercivity. When you are making electromagnet, that is temporary magnets, then you look for lower retentivity, lower coercivity. And when you are looking at transformer cores, that time the area of the hysteresis curve should be smallest, because the heating there becomes the prime important thing. So if you look at the options now critically, then you realize that B for electromagnets because its retentivity is less and coercivity is less, and transformers because the hysteresis area is less. Okay, that satisfy the criteria most appropriately. The remaining answers you will look. A for electromagnet is overruled. A for transformer is straight away overruled. Fourth, A for electric generators. A for electric generators and transformers. So transformer desires smallest area, so the option would be free. Once again, a very simple question, no information, no calculation is required in this one. Okay, let us come to the next problem, that is 77 problem. Again, a very common problem, the common question in the sense, because this aspect you discuss in two chapters. You discuss in a simple pendulum, that is simple SHM, simple harmonic motion, and you also discuss the concept in heat and thermodynamics, that is when you are reading the expansion. If you recall what we had studied, we studied T is equal to 2 pi under root of L by G, then T prime at some temperature becomes equal to 2 pi under root of L prime by G, and if there is a change in temperature, we say T prime is equal to 2 pi under root of L theta divided by G, and this L prime can be written as your L0 1 plus alpha delta theta, where delta theta is change in temperature. This term you already know it to be T, so T prime by T becomes equal to under root of 1 plus alpha delta theta, and if you bring it here, you get delta T by T is equal to 1 by 2 alpha delta theta from binomial expression. So we are going to use this result straight away, that is change in time period is equal to 1 by 2 alpha delta theta into the T. This is what we are going to look at. Okay, so let us start now with a question. It says a pendulum clock loses 12 seconds a day if the temperature is 40 degrees Celsius. So the first thing is, when do you lose? When do you lose? You lose when the time period becomes more. And when time period becomes more? The time period becomes more if the length becomes more than the calibrated value. Okay, so now he has told you that the temperature is 40 degrees Celsius. If the temperature is 40 degrees Celsius and the calibrated temperature, let us say, was theta, so he has given you how much you have lost. You have lost 12 seconds. So you will say 12 seconds is equal to 1 by 2 alpha, and 40 is the temperature, and the calibrated value of temperature was theta, for which it was designed. Now in the second case, he tells you at the temperature of 20 degree you gain 4 seconds. If you gain 4 seconds, what does this mean? It means that your clock is running faster. If it is running faster, that means time period is reduced. If the time period is reduced, the temperature is below the standard calibrated value. So he is telling you 4 is equal to 1 by 2 alpha. There will be a day period, so you write that as T, you write 24 hours, you write it in second. That term you are going to cancel as it is, so I am keeping it T as it is. Alpha, this will be theta minus 20 multiplied by T. So if you simply divide this, you can lose this term, this term, this term, and this term. and this also can be lost. So the 3 theta minus 60 will be equal to 40 minus theta. Shift it there, shift it here. 4 theta is equal to 100. So theta is equal to 40, okay, 100 by 4, that is equal to 25 degrees Celsius. So this must be your calibrated value for which it is designed. So if you look at it, what has he asked you in the question? The coefficient of linear expansion alpha and the temperature. So if you look, only the correct answer is 25, you don't even have to calculate alpha, that is not required, because if you are concerned only with the answer, then the fourth answer is correct, because 25 is coming in one of the answers. Otherwise alpha also can be calculated, because at day's time you know how much is day's time. If you come here, put the value of theta, put the value of t in second, then this 12 will cancel with that second, and that will give you the alpha. So unnecessarily calculation is not required as long as we are interested only in getting the question right, right? All right.